Hello, welcome again. We are covering the subject steam engineering for civil services mains, IFS and various gate exam. Next topic in the chapter of flow through nozzle is velocity of pressure pulse in a fluid or velocity of sound in a fluid. Suppose this is your piston cylinder arrangement, and in the cylinder there is gas which is stationary initially, having pressure P, density rho and enthalpy H. Now small displacement is given to the piston so that the piston moves by an amount dV, and it creates a pressure pulse with moves with velocity c. Okay. So as this uh, pressure pulse moves in the gas, it changes the condition of the gas. So here the condition of the gas is, or pressure of the gas is P plus dP, and density is rho plus d rho, and enthalpy is h plus d, and it also gains velocity dv, that is the velocity of piston, and here the gas is stationary. So all this we are observing when we are stationary and wave is moving. Now to analyze it or to simplify it, what we do, we start moving with the wave. Okay. Then this stationary gas, if we are moving with the wave, then this stationary gas appears to come to us, okay, with velocity c, and here the gas is leaving with the velocity c minus d, because here the velocity of gas is dv in this direction, and here from here the gas is coming with velocity c, so net velocity will be at c minus d. Okay. So now we are moving with wave, so this gas appear to be moving towards us, and with velocity c or velocity, and this gas appear to be leaving the wave with velocity c minus dv. Okay. So now we can apply here the continuity equation. So continuity equation is mass flow rate is constant, so here mass flow entering to the wave is rho AC, and here mass leaving the wave is rho plus d rho into area into c minus dv. Okay. So if we solve it, then a will cancel out, so here we rho c, and here we rho c, minus rho dv plus c d rho minus d rho dv. So this is product of two small quantities, so it can be neglected, and rho c will cancel out, and now we'll have only these two terms, and these two terms will be equal, because equal, and the equation will become rho dv is equal to c d rho. So this is equation number 1. Now we'll apply the momentum equation. For momentum equation, there is one side there will be force, and other side there will be rate of change of momentum. So net force is, initial pressure is P, and final pressure is P plus dP, or the pressure on the right side is P, pressure on the left side is P plus dP, and multiplied by area is force, and that should be equal to rate of change of momentum. So final velocity is c plus c minus dv, initial velocity is c, and mass flow rate is your rho AC. So c will cancel out, so a will cancel out, p will cancel out, so here it will be dp by c, and here it will be rho into dv. Minus sign is there, so minus minus will cancel out, so rho dv is equal to c0, so dp by c will be equal to c by d rho, or c will be your root dp by d rho. Okay. So this is the expression for pressure wave, or velocity of pressure wave, or velocity of sound. So as here we can see that the process is taking very fast, taking place very fast, so there is no time for heat rejection, so we can assume it as adiabatic process, as the changes are very very small, dp, d rho, dh, so it can be assumed reversible, so it is reversible adiabatic process or isentropic process. So C is your curly root curly row by curly p by curly row entropy constant. So if we apply it for ideal gas, for an ideal gas and for an isentropic process, PV raised to gamma is constant, or P by rho gamma is constant. Now we take log and perform differentiation, then dp by p minus gamma d rho by rho is equal to 0, or dp by d rho is equal to gamma p by rho. Okay. So C square will be equal to, as C square is equal to dp by d rho, and dp by d rho is gamma p by rho. Okay. So or from an ideal gas, this P is equal to rho RT. So it will be rho RT by rho will cancel out, or be gamma RT. So C square will be your root gamma RT, because this is dp by d rho is your C square, so C will be your gamma RT. So this is the expression for phonic velocity, or velocity of sound, or velocity of pressure wave in any medium, okay, or in an ideal gas. So I will read out this for you. The topic is velocity of pressure pulse in a fluid. Let us consider an infinitesimal pressure wave initiated by a slight movement of a piston to the right in a pipe of uniform cross section. So this is a uniform cross section pipe, and this is cylinder piston, and it is moved by small displacement with velocity dv. The pressure wave front propagates steadily with a velocity c. This is pressure wave front, which is known as velocity of sound, phonic velocity, or acoustic velocity. The fluid near the piston will have a slightly increased pressure and will be slightly more dense than the fluid away from the piston. So here the wave has passed, so here the pressure, density and enthalpy and velocity will also change, and here it will remain because the wave has not reached up to that point of the pipe. So to simplify analysis, let this is sonic velocity with stationary equation. To simplify analysis, let an observer be assumed to travel with velocity c. The fluid flows steadily from right to left as it passes through the wave front. The velocity is reduced from c to minus c minus d. So as this will seem stationary, so it will be c, and the velocity will be reduced from c to minus c minus c minus d. At the same time, the pressure rises from p to dp, p plus dp, and density rises from rho to rho plus d. The continuity equation for the control volume gives, so this is continuity equation, that is rho AC on left on this side is equal to rho plus d rho into a bracket c minus dv, or solving it will be equation number 1. Okay, so that is rho dv is equal to c d rho. Now from momentum equation we have p minus p plus dp within bracket a is equal to rho AC bracket c minus dv minus c, or from this 1 and 2 dp by c is equal to c 0 and c is equal to root dp by d rho. Since the variation in pressure and temperature are negligible small, and change in state is so far that essentially adiabatic, and in the absence of any internal friction viscosity, the process is reversible and adiabatic, hence the sonic velocity gained by this. Okay. So now for perfect gas, for ideal gas, PV raised to gamma is constant for isentropic process, and by logarithmic differentiation we got this, and then we got c square as dp by d rho, and c as root gamma r.